Rest of the slide in this chapter, and we will talk about correlation structure. Okay, and when we go back to mixed effect analysis, and we have step 1 and step 2 and step 3, and then at the step 1, and we saw a box we usually don't see in SPSS, which say repeated covariance type. And then here I ask you to set it to unstructured so that we can reproduce exactly the same analysis we did with paired sample t-test. And unstructured is not just a choice and you can use. And there are in fact, okay, let me go to mixed effect model. And again, we need a longitudinal format for mixed effect model. And we go to mixed model linear, and here is the choices, and you have 15 different choices and you can make. It depends on software how many choices are allowed to use. If you use SAS, and you have probably more than 20 or 30 even choices to pick from. And so, using rest of the lecture note, I'm going to explain what these choices are and what the difference is and why it's important to consider this covariance type structure, this covariance type. Okay, so let's go back to, so I'm going to explain, actually I don't have time to explain all 15. Therefore, I picked ones more commonly used method than others. So we will talk about scaled identity, and we will talk about unstructured and top limits option and compound symmetry in AR1. Actually this one, okay, AR. Alright, so those are the methods we are going to talk about today. And then before we talk about correlation, covariance type, which is the same thing as we will talk about correlation, and why it's important to know correlation among repeatedly measured data. And because of this, so let's go back to this slide. Okay, so correlation actually linked directly to variation among patients and variation among within patient difference. So when we have repeatedly measured data, total variation consists of these two variation between patient and within patient. And when you have larger correlation, that means between patient variations are much larger than within patient variation. And what does it mean? That means repeated measures are a lot more stable within patient over time, okay, given patient variation. So here, this data has a lot higher correlation, and dental growth measures are more stable measurement than CRP. Therefore, it doesn't change as much within patient compared to CRP data. And the analysis we focus is really what happened within patient. And we are not really comparing what happened among patient, right? Because we want to know dental growth measure change of this girl when she was 8 and she was 10. So analysis should focus for within patient variation. But in order to focus on within patient variation, we have to remove between patient variations. Okay. So one way to remove between patient variation is to model correlation. Okay. So higher correlation and you have more stable measures. More stable means much higher between patient variation than within patient variation. So in order to focus within patient variation, okay, we are going to model correlation between repeated measures. Okay, so that's one way to remove between patient variation from data. I want to convince you with this point because this is very important, right? And this is the data set. I'm using CRP as an example, right? So these black dots are coming from a single patient, and then while this person is in hospital, and then you measure CRP level every day, okay? And then you wonder if the catheter, using catheter, increase degree of inflammation. So this day, this patient used a catheter, and then you see CRP increased. And this is another patient. Okay, red are from another patient. And this person has relatively lower CRP. But again, when the catheter was placed, CRP was increased. Okay, so by looking at this data, what do you think? Do you think catheter has association to inflammation? Probably yes. And how about this data? Okay, so this black is measurement within a patient, and then red is measurement within another patient. And this point, this is the day this patient used a catheter. This is the day this patient used a catheter. Okay. And what do you think? Do you think catheter has effect of increasing inflammation level? And probably not. And so let's think why you thought there is no association with this data, but there is association with this data. And what probably you thought is, given this CRP level within this patient has a higher CRP, but within this patient, CRP is actually stable, right? So it is similar, although only when catheter was placed and it increased, right? And again, the same thing. This patient and inflammation level seems stable, but only when catheter was used and CRP level increased. Here, and amount of increase in CRP is actually the same, this point and that point. Okay, so catheter, where the catheter is pointing is the same, right? But you thought there's association here, there's no association here, because with this patient, and you thought inflammation level is all over, so you can't really tell increasing in CRP here is due to catheter or not. So this indicates low level of correlation, and this indicates high level of correlation. So when correlation is high, that means a lot more between patient variation. Okay, a lot more between patient variation compared to within patient variation, a lot small, right? Within patient variation is a lot smaller. It's here. This is within patient variation. And here again, within patient variation is much smaller. So when the correlation is very high, then data are more sensible to pick up a difference by catheter. When you have a lot more variation within patient, okay, so now you have a lot higher variation within patient, and then model become insensitive to pick difference by catheter. So it is very important to model correlation, degree of correlation, in order to make inference between catheter and CRP. So that's why I have about 10 more slides, and we will be talking about structure among this correlation. Okay, so let's look at correlation between dental growth measurement between each of two time points. So at age of 8 years versus age of 10 years. All right, the correlation is 0.889. So I'm only doing a Spearman correlation. Okay, so what I did is, okay, to do this, we go to horizontal data set. And what I did is just go to correlate, bivariate, and put everything in here. Right? You can do Spearman, but we are talking about parametric model, so I'm just that's the reason I'm doing Pearson. And click go to Pearson. Okay, so here, so this table is the same as the table we had in the lecture note. Okay, so this correlation is correlation between dental growth measurement at between age of 8 and 10. This correlation is between age of 8 and 12, and this is between age of 8 and 14. This is between 10 and 12, and 10 and 14, and 12 to 14. So you have six different values for correlation, because we have 6 different pairs. So our goal is, and again, our goal is to find a parsimonious structure among these correlation. Okay. And because in order to compute effect of this example age, or could be effect of CRP, and we had to model correlation between repeated measures. So the best model we could probably use is simply exactly compute Pearson correlation between each pair and then use this number. And although these we are actually measuring 6 numbers, okay, the more number we estimate, we lose power. So the goal here is for somehow, and we like to find the most parsimonious structure among these 6 numbers, okay, and which explain much variation in data, and which actually fit relatively good to data without measuring these too many parameters. Okay, so 6 is maximum here. So let's see if we can reduce this number of parameters and still we can maintain good fit to data. And so if you have no idea and the only thing you can do is just let SPSS compute exact correlation. So if that's what you want to do, and you choose unstructured as an option. So when you go to SPSS, mixed effect, okay, and here let's put ID. I need the longitudinal data, by the way. I have to go back to gross long and go to mixed model, and here, right? So this unstructured is the choice if you think this correlation is the best parsimonious sets of the numbers. And next type of correlations, and we allow 100% correlation for the same values. That's of course, right? And correlation between the two same variable have to be 1. And then the correlation between the different values. So dental growth at year 8 and 10, and 8 and 12, and 8 and 14. So all of diagonal correlation. Okay? And you assume there is no correlation. Okay. So 1 or 0. And so this is called the scaled identity. And by the way, if you ignore dependency among repeated measures, and you don't really believe measures coming from the same girl are different from measurement coming from another girl, then you might want to use this. Okay, that's what linear regression is assuming. So if you want to perform linear regression using SPSS, okay, you can do that. You simply pick scaled identity. Okay, so that's your assuming observations from one girl is as different as observation from another girl. Alright, so let's move on. By the way, this is a pattern graphical presentation of independent. You can predict gross measure at next time point and given the previous time point. See, it's a chaotic pattern. And the next one, exchangeable, and SPSS called this compound symmetry. And compound symmetry is a correlation structure. You assume correlation between any two time points are the same. R is a correlation coefficient. It's a number between -1 and 1. I mean, it's hard to have a negative correlation of repeated measures. So R is usually a number between 0 and 1. So here you are saying correlation between measurement 8 and 10 is the same as correlation between measurement 12 to 14 or 10 to 14. So let's say how many parameters here you reduce number of parameters. It's only 1, right? And how you estimate this? You simply take average over these original 6 measures. So if you take average of this number and then replace all these number with average. And that's probably hard to believe, right? So you think dental growth measurements at the two time points closer to each other should be more correlated than the two measurements, and which are much farther apart to each other, as you see here. In this one, 12 to 10, 10 to 12, and 12 to 14 has a much higher correlation than these correlation with a much apart time points. But that's one of the structure. And another structure is called auto-regressive, first order auto-regressive model, which SPSS is calling as AR1. Okay, so this correlation structure, you only estimate one number, but you allow the model to weaken the correlation as interval between two time points getting larger. So let's say, and R is a number between 0 to 1. So if the R is 0.9, and 0.9 to the power of 1 is 0.9, 0.9 to the power of 2 is 0.81, 0.9 to the power of 3 is 0.73, I think. Okay, so you allow model to weaken correlations with the distance between two time points gets larger. Right? So how many parameters you estimate here? It is 1. Okay, so it's much better than estimating 6 different numbers. Okay, so this is the graphical patterns for first order autoregressive correlation. And okay, I'll get back to heterogeneous later. And top list the options, and you allow different correlations, and without assuming this power relation. Okay, so here you have ABC correlation between two time points, and a distance is the same. So 8 and 10, and 10 and 12, and 12 and 14. Distance is 2 years apart, right? And then you assume those correlations are the same. And the correlation between this time point, so that's 8 and 12, and 10 and 14, 4 years apart. And then you assume a different number for correlation. And then here is the two time points and apart by 6 years, and you assume a different number for correlation. And then there's no structure among ABCs. And here, how many parameters are you modeling? It's 3. Okay, it's still less than 6. So there are many choices for correlation among repeated measurements. And so you might wonder what correlation we should be using, because choice of correlation does have an impact on p-value. So if you have a wrong guess for correlation, and then you end up having a biased p-value. Okay, so here is a quick guideline: selection of correlation structure. If the number of repeat is small related to number of patients, and then unstructured matrix is probably better. So again, why we want to go parsimonious, and we want to preserve power. So if you have many sample size, that means you have enough power to build a complex model. So you might go ahead to model all 6 parameters, which is unstructured. Okay? And if the observations are measured over time, and then you probably want to use a structure that accounts for coordination as a function of time, and for example autoregressive. So that model can weaken coordination since as interval between two time points get larger. Okay, and lastly, if observations are clustered, so that means you don't really have a notion of time in terms of repeated measure. Okay, then compound symmetry option may be appropriate. And for example, a lot done in basic science, and you repeat your measurement 3 times for each sample within a short time point, and the purpose is not really trying to assess difference by time, and you just want to improve accuracy of a measurement. Then you probably don't even record which one was measured first and which one is last. So you don't really care order in time. And then those data, we call it clustered. Okay, and those clustered data, and we might use compound symmetry as option. So now you may be wondering, what should we do with so many selections? Should we perform 15 different correlation structure and pick the ones providing smallest p-value? And that's a big taboo. We shouldn't look at p-value to select what is the best structure. And instead, there's a quantity called AIC, Akai Case Information Criterion. So you go ahead to run the model with a few selected correlation structure. I wouldn't check with all 15, probably 3 or 4, and you check and then run the model with each structure, and then you might select structure providing smallest AIC. So what I did is I go ahead to conduct mixed effect model. Okay, so you go to mixed model linear and put the ID under subject and age under repeated, and let's pick the one with unstructured then, and then go ahead to continue. And growth is a dependent variable, and age, we want to compare mean of growth measures between each point of age. So we put age as a factor, okay? And then put the age under the model in the fixed effect box, right? And go ahead to click OK. And if you go to SPSS output and look at the table called information criteria, and you can get AIC from this box. Alright, and then repeat analysis with other correlation structures. So here, and let's go to do AR1 and continue and OK. And that gives AIC is 129. Okay, so AIC is 129. So I repeat this with three other compound symmetry and scaled identity and toplets. And then let's compare. So it looks like RA1 auto-regressive, first order auto-regressive is giving smallest AIC. And let's look at compound symmetry, that's the second smallest, and then third smallest is unstructured, and then fourth smallest is toplets, and then the worst one is scaled identity. So data are repeated, and therefore you would not assume scaled identity. Scaled identity means data are all independent. So you know that's obviously wrong choice. Okay, so you might be wondering why it's not unstructured, and we thought unstructured give a best fit. So what happened with AIC is AIC, you get penalized by including many parameters. So we know unstructured is a best provide a best fit, although it consumes 6 parameters. Okay? And so AIC, so what AIC is telling is auto-regressive option, first order auto-regressive correlation structure, and you consume least number of parameter, and then yet to achieve pretty good fit. Now we know we are going to use auto-regressive AR1 for correlation option. So we go ahead to repeat the analysis, okay, and with auto-regressive option. So mixed effect, linear, and pick AR1. Yes, we already did that analysis. And then now you can check p-value. Okay. And so let's look at type 3 test for fixed effect, and which provide ANOVA type p-value. So this means at least one of the time point h growth measures are different from another. Okay, and you can look at parameter estimate. So here, and you see pairwise difference in age 14 years being a reference category. And all p-values are significant. So between age 8 and 14, it's significantly different. 10 to 14, significantly different. 12 to 14, it's significantly different. So that's the result of this analysis. Last thing, and we have to check, is residuals. Mixed effect actually do assume normality in the residuals. So it's similar to linear regression because this is a parametric model. So you go back to mixed effect model. And so let's create residuals as a variable and paste into working data set so that we can check distribution of residuals. So you go ahead to click residuals, okay, and continue and OK. So now you have residuals created. So how we check normality? And you go to analyze, descriptive, and explore. And if you put residuals under dependent box and keep display as a bourse and go ahead to click plots and we want the normality plot with p-value. So click that one, and we want the histogram. Okay. Alright, so residual seems very normally distributed. Its box whiskers plot is symmetric, and QQ plots, dots are nicely lying on diagonal line, and histogram looks pretty normally distributed, except for this cluster, but I think it's okay. And so we can present this mixed effect model. Alright, so this is the end of the analysis comparing gross measurement, average of gross measurement between different age groups. And in fact, okay, and if you look, okay, so this plot show the mean of gross measurement at each different time points, age. Okay. And if you think it's okay to put the straight line over this different age, and you may want to model age as continuous variable. So what SPSS would do is go ahead to put the straight line, okay, and within each individual patient, and then sort of take average of the slope. So here, if you put the age under covariate box instead of factor box, and you end up having only one beta coefficient. So this is different. If you put the age under categorical factor box, and you have three different beta coefficients, so 8 to 14, 10 to 14, and 12 to 14. But if you put the age under covariate box, and you have only one estimate, which is a slope. So what is a slope? That is an increase in gross measurement by 1 year of age increase. So that is annual rate of increase in gross measure. All right, and that's average over 10 girls. Okay, so you can say, so that makes sense? Yeah, 8 to 14, 6 years. It looks like increasing about 3, yeah, 17 to 20, probably that's average slope. And so that's this one, okay? So annual increase in gross measure is 0.5 millimeter among these 10 girls, and which is statistically significantly different from 0. So slope is not flat, and we can say there is association between age and dental gross measures. Okay, that's it for today. And in next video, and I'm going to introduce you the different technique of using mixed effect model, introducing random effect. Today our analysis focus on correlation structure, but next video, and we will focus on random effect, and that may be new terminology. So I will see you in the next video. Goodbye.